We are back here in our lecture for CSE 455 Software Engineering. We are meeting today, Monday, the 18th of May. So let's proceed. Let me remind you first of what we have gone through last week or last Sunday. I have approve your SRS and ask you to get the approval of your clients. So far, three teams have not obtained the approval of their clients. The Breath of the Coyote, the iBox, and the UDRAP. And all SPMPs have been approved. You've done well in the planning and the software architecture and design document, which was due yesterday, Sunday, the 17th of May. Note that the design and coding is a cyclic process. You go and fix your design, uh, continue coding, or you fix the coding and continue design. So the design will be, excuse me, will be a cyclic process because you will be constantly fixing your design and continue coding. Okay. The delivery of the first iteration and QA testing will occur this week, 18th up to the 24th. So you will have to do this online with the QA testing, and we have looked at the procedures of the QA team. So when a development team is ready, they will inform the QA team that they are ready for testing the prototype 1 or the first iteration. QA team will access the development team repo, and the QA team will check whether the software artifacts, SRS, SPMP, SAD, software architecture and design, and source code are stored in the repo. The development team will give instructions to the QA team how to compile and build the executable object module. So QA team will create and install the executable object module to a mobile device for testing. So you shouldn't give the QA team the executable object module, they will build it. And if they fail to build your executable module, then you are not ready for testing. So the testing can't begin if they can't create it. The QA team will then perform testing on your prototype 1, and when they are done, they will submit a test report to the CEO. And after review, a copy of the test review will be given to the development team. And we talk about uh, issues, or if you pass, then that's a good achievement that you have passed the QA team. The development team will get a pass if all of the criteria of the test report are satisfied. Okay, so it's all or nothing. That's the criteria for passing the QA test. And what are the criteria for the QA test report? Um, you must pass all the functional and non-functional requirements. They should uh, test your uh, use case and all the associated user interface for that use case. And they will try test cases on your functional requirements, and also the non-functional requirements. Uh, the non-functional requirements we always specify on the SRS is the performance. So it should respond to the user's request after hitting the return button is 2 to 3 seconds. And then after that, uh, there could be other non-functional requirements like usability, um, maintainability, security, and others. Um, is the software artifacts complete? So they will look at your software artifacts and answer it yes or no. So completeness means do you have the high level design? Do you have the low level design? And do you have the detailed design? So those are the 3 levels of design they will look for. Next one is, did the development team follow the coding standard? Yes or no? So they will look at your code, whether it is in Java or Objective-C. They will look and see if you followed coding standard. And coding standard is a good practice for maintaining software. The readability is supported, and hopefully would help the next team to continue your work. The next one is they will try to see if your team has performed verification and validation process. And this process, verification and validation, consists of unit testing, integration testing, system testing, and regression testing. So you must give evidence that you have done this. How? By giving test cases, samples of test cases you have used in the unit, integration, system, and regression testing. So they will answer yes or no if you have evidence that you have done this. And the last one is, did the development team collect metrics um, from the development from you, from the development teams? Did you gather productivity metric? What's the number of LOC lines of code that you produce per hour? This is for the entire team combined over the entire team of coding plus design plus debugging. All of this will be included in the time to determine the number of lines of code that you produce. And the quality of code metric, this measures the quality of the code that you produce by uh, telling us what's the number of faults that you have per 1,000 lines of code. Okay? All right. So the just a reminder about the software architecture and design. Let me just show you that again. So you have the title of the document, Software Architecture and Design, called SAD, and project name and the date, who is the project manager, who is the assistant project manager, and this is the responsibility. Writing this document is the responsibility of the management team, consisting of the project manager and the assistant project manager. And the software engineers, the management team is responsible for the high level design, and the software engineers are responsible for the low level design and the detailed design. Okay, so it's a combined effort of the design document. The the purpose of the document is, of course, determining the structure and outline of your software, uh, but it is very important in maintenance. Um, as I have said before, it is easier to understand UML diagrams than to read thousands and thousands of lines of code. And this helps in the maintenance of the software. So the SRS combined with the software architecture and design will help in the continuation of the project after this class is over. And it is true in many software that we see today. It is not a throwaway project that you see in your ordinary course, like compilers, operating systems, um, database. After the project is over, you throw it away. Okay, not in this class. In this class, you continue previous year or previous years of project that was done, and you are continuing their work. That's the real world. So when you join a software company, you will work 99.9% on existing products. You will be maintaining the current software that they are maintaining. Okay, so you will always deal with software artifacts and continuing the project, improving it, correcting it, and adding more features. That's how we define software lifecycle. Software lifecycle never dies. Software remains for many, many years, depending on how good the software is, it will still remain to be used. So maintenance is, I believe, the most important phase of the software lifecycle. Without it, you don't have the software improving or continuing to serve its purpose. I define architecture and design into three levels. We have the high level design, and the high level design usually is um, the, uh, uh, the techniques that we use to break the software into its sub components. That's what we call in computer science divide and conquer. That's hierarchical decomposition or top down. That's usually what we do when we try to um, uh, find a good way to uh, define the structure of your software. Another very good architecture is layered architecture. And layered architecture could be 3-tier or 4-tier. And Usually in a 3-tier or 4-tier, the lowest level is the one that is closest to the hardware. And the top layer is the one that's concerned with the application, the database, or any application. And the middle in the 3-tier and the 2 layers in the 4th tier are middleware software. So this is also very useful um, architectural style that you use in high-level design. There is also the client-server architecture, which is used in many applications that we have today. So the software design consists of a client and a server, and you usually have this in um, database or in web server requirements, and the server gives service to the client. Another one is the repository architecture, and the repository contains all the information that you need, and um, it provides you with um, standard service like get or put or delete or insert um, into the repository. So repository performs, or you store all the data structures in the repository, and gives you all the service. Also very nicely used or very often used in database. And the model view and controller MVC architecture is used in web building web application. Consists of 3 components: model, view, and controller. So you may use any combinations of this architectural style, and the unit of the design could be a package, a module, or a package, module, or an object. Okay, so that's uh, your unit of design. Okay, so um, this architectural style, if you represent the um, uh, the major components of your system as package diagram, component diagram, or module, they are high-level design. Okay? Now, once you start decomposing this high-level design um, into its class diagram, if you uh, understand a package or a component or a module into the class diagram um, decomposition, then it becomes low-level design. So the low-level design consists of the class um, itself, its visibility, list of member variables, and list of member functions. And that's the member functions or methods inside the class. Then that becomes low-level design. And this class diagram uh, is, is shown inside a component diagram or a package diagram, where it was defined in the high-level design. So once you decompose the a package diagram or a component diagram into classes, they become low-level design. Okay, and we do this for each of the component or package. And then finally, um, when you reach the pseudocode level or the member functions of the um, class, you select for each of the member functions or methods that are critical. Now remember that not all of the functions you will have to detail. You will detail the important functions that is inside the class, and you use pseudocode in depicting the logic behind the function that you have um, identified. So uh, this is used in analysis of the correctness of the function or the method. And as I said before, fixing pseudocode is much easier than fixing source code. And if you fix the error in the pseudocode, the error or fault will not appear in the source code. Okay, that's the idea. So this software architecture and design consists of three levels: the high-level design, the low-level design, and the detailed design. Okay? Uh, Hope you understand that. And let's proceed to the next part. Okay. Um, Let me, before we do that, I would like to go back and talk about more about the pseudocode. Okay. Okay. I lost the cursor. Let me. Okay. Let me go over here and show you this one here. Okay. Um, Here is the example I gave you last time. You can start from the deployment diagram, and from the deployment diagram, you choose which component you want to um, decompose into its subcomponents. And you see over here that this component was decomposed into two components. The B components is decomposed into B.1 and B.2 over here. And then the B.1 is decomposed into class diagram. So the class diagram is um, derived here, and the class diagram is consisting of four classes: B.11, and the sub classes are B.1, .1, and the other one is B.1, .1, .2. and b dot 1 dot 2 is the other class. Okay, and then for each of these um, class, we define the functions inside the class. So there's F1, F2, up to Fn. Those are the methods. But for those important functions, we can write the pseudocode for that specific function. So the pseudocode does not follow the syntax of the language, but it is easy to follow the logic by um, um, writing it in some high level language that you can understand, okay, and follow the logic. Okay, so uh, let me show you then the here it is. Okay, if you remember, we talked about the elevator problem, and there is a method that is useful in the uh, in the class for elevator control. And the elevator control, as you can see here, it's written in some high level language or pseudocode. So you although it looks like C, but um, uh, the other parts of the algorithm of the pseudocode is not really following a syntax of the language, but it shows you the overall logic. So the overall logic here is uh, a case statement where you have several cases. Right, like here, the first case is if a button has been pressed and if the button is not on. This is what you'll do. Here is another case, else if the elevator is moving up. This is what you'll do. Else, this is what you're going to do. The other case is the elevator is moving down. So the, the previous case is elevator is moving up. Here, elevator is moving down. And the see here, the pseudocode, it says similar to the up case. So that's understood that you will just repeat the logic if the elevator, if it is stopped, then it should move one floor up, in this case, one floor down. And otherwise, you follow this set of logic of the elevator moving down. So else, if the elevator is stopped and request is pending, then we close the door, and if the floor button is on, then floor button turn off. And as you see here, we follow the constructs of the language, like if, then else, um, uh, for loops, um, uh, the begin and end of a program we represent as open brace and then close brace over here. And the representation of an infinite loop is a do without any condition for exiting. So it's very easy to understand and fix pseudocode. Okay, uh, pseudocode is um, clearly understood, and you can subject this to a paper tracing to see if it works. Okay, so keep this in mind. The pseudocode is much simpler than following the syntax of a language. So try to do this in your detailed design. And the detailed design can be tested for errors before the source code is written. Okay? All right. Now, let's see. Let me get out of this. Okay. And let's continue to the next slide, which is the um, reverse engineering. Right? And last time I started with okay. Okay, I lost my cursor again. Let me do that here. And let me show that to you right here. Okay. Here it is. Okay. Um, hmm. Let me start with showing you the article on reverse engineering. Okay. All right. So, what is reverse engineering? Reverse engineering, also called back engineering, is a process by which a man-made object is deconstructed to reveal its designs, architecture, or to extract knowledge from the object. And similar to scientific research, the only difference being that the scientific research is about a natural phenomena. Okay, um, so this is a man-made object. It's kind of a generic term used here, and you want to deconstruct to reveal its design, architecture, or to extract knowledge from the object. Okay, so let's look at the reverse engineering of software. And the uh, the IEEE define reverse engineering as the process of analyzing a subject system to identify the system's components. We want to find system components and interrelationships to create representation of the system in another form or at a higher level of abstraction. So the keywords here are we'd like to identify the components and their interrelationship. So we can represent the system uh, in another form, and in our case, we want to um, um, extract the abstract representation of this software. And we began uh, talking about this last time, and I was uh, showing you the um, the way. Um, oh, that's not what I'd like to show you. Uh, where is that? Here. Okay. So reverse engineering, you have the source code, but you don't have the design. Okay. So you want to reverse engineer the source code um, to extract the component and the interrelationship among components in the um, uh, in the software. Okay. And you've seen this example here from my previous lecture. So let us say from the source code, I'm able to determine the classes because that is well represented in the source code. You have a definition of a class, the member variables it has, the member functions it has. Okay, so let us say this is um, the class diagram that you extracted from the source code. And you can do that. You can read source code and you can represent each class as a name of the class, the member variables, and the member functions. You can also identify inheritance in the source code. You have a superclass and you have subclasses. And then you have associations. That is a class accessing or sending message to another class. You can determine that through the parameters or through the objects that it calls. So you can create this class diagram as you see over here, right? But you have to read the code and extract the classes and what messages does it transfer between class, okay? So you apply the principle of cohesion. So you set a boundary over those classes that has a strong cohesion. And what does it mean? Strong cohesion means the relationship among classes in that boundary are strong, like this, for instance. The customer, corporate customer, personal customer are all related to each other by subclass or inheritance relation. And you see here that employee, which is another class, is also kind of related to this uh, inheritance that you see over here. So it's very logical to draw a boundary around all of this set of classes. So we call that one um, component or one module of the software. Over here, looking at the name, order and order line has a relation. They all pertain to order. So they are related, strongly related, because of the function they are supposed to do. One order here pertains to the entire list of order, and the order line is kind of a a detail of one of the order lines. So they are related, and therefore we draw a boundary around them, and cohesion is high here. And the product itself, we could not find any strong cohesion um, with the other um, boundaries. We have it as just uh, one element um, um, in this package. So once we draw the we draw the boundaries, we identify three components. And if you remember, we have uh, we have in this next diagram the packages that would group all of those classes into three packages. Class A, class A, I mean component A for this boundary here. Component B or package B for this group here. And finally, the only single class in that uh, group, we call it package C. And we see the uh, uh, the communication or interrelation of A and B with uh, a unidirectional communication from A to B, and that is represented here by this um, association from order to customer line. See that? Okay, over here. And then from order line, there is a association from order line to product. And so that's where those arrows come from. And the last step is to uh, convert this lines into the following. Okay, right here. So those communication lines become ball and socket graphics representation. So what does the ball means? A ball means I provide service to other component of package. And a socket, this open symbol here, open line and a semicircle, is a socket. The ball fits inside a socket. So the socket represent I need service from another component or package. So ball, I provide service. Socket, I require service. So from the previous diagram that you see before, instead of a line with an arrowhead, we have a ball and socket graphics representing what is needed by a component or a package to another component of package. So this becomes a completed diagram from um, the reverse engineering of the um, class diagram that you have. So instead of reading hundreds of classes, you can reduce the um, the number of elements in your design into lesser number of units like packages. So here it is readily understood that it consists of three packages A, B, C, and that's how the relationship exists between packages. Okay? All right, let's move on. Now, supposing after you have read the source code and determined the packages in um, in that source code, you came up with 10 packages right here. And you determine the, uh, uh, the association or the interrelation between packages. So those lines that you see over here with the arrowhead, that determine or that shows you which particular package needs service from another package. Okay, the ball and socket. All right. So next thing you need to do after looking at this 10 packages is to draw boundaries around these packages. Okay, and your principle of cohesion comes in. Why did I put a boundary between these two packages here? So your logic will be to determine what is the relation between these two packages. Are they strongly related? Are they helping each other to perform a function? Then if they are, then you put a boundary around it. These three packages that you see over here is uh, the same principle. The three packages were determined to have strong relation with each other. And the single package that you see over here is by itself. And the last four packages are helping or collaborating with each other to perform a certain function. So we identify here four packages or four components. So out of the two packages you see over here, we have a single one called A, and the three packages on your right is represented by B. The single package that you see over here, right here, is identified as C component, and the four that you identified over here is this one. Okay, now converting the directional lines that you see above, you see that A provides service to B, and B needs that service. So we have a line going from, or we have a ball on A and a socket for B, and that is represented here, that this entire component needs service from this package here and this package over here. Okay, so that uh, that requires service from these two components that you see over two package that you see here. And notice also that this component here, I mean package here, requires service from these three other packages also here. So the the B component provides service to C, but it needs service from A. That is why you have B as a provider and a need for service from another component. So from A, it needs service from A, but it provides service to C. Okay? Now the four that you see over here, let's convert this directional lines here into its ball and socket. And you see over here that we have converted them into ball and socket. So between this package and this package, the left package provides service to the right package. That is why you have a ball over here and a socket here. And this package here on the left needs service from this package. So it is both a ball and socket. It provides service and it needs service. And then finally, in the lower package, it needs service from this right package here. Okay. All right. And that completes the ball and socket of the bottom boundary. And finally, the diagram is completed here below, showing all four components A, B, C, D, with component D not requiring any communication with the other three components, A, B, and C. Okay? So that is reverse engineering, and probably most of you will have to look at the source code, draw the class diagram, find out which class diagram communicates with another class diagram, then make boundary lines among classes that are collaborating or are strongly related to each other. So that forms a group of classes belonging to the same uh, package. Once you determine all the packages, you again repeat the procedure by drawing boundaries around the packages to form a higher um, group of, um, we call them components. So the components form a higher level of composition, and then you connect them with ball and socket linkages. Okay, so that's reverse engineering of trying to extract the structure of the design and their inter um, relationship. Now, uh, let's continue uh, the discussion. Reverse engineering by going back to the article reverse engineering. Reverse engineering is a process wherein we deconstruct to reveal its designs, architecture, or extract knowledge from the object. And reverse engineering is applicable to mechanical engineering, electronics engineering, software engineering, chemical engineering, and systems biology. So it is the process of extracting the designs and architecture or to extract knowledge. What is the object all about? And our interest in reverse engineering is reverse engineering of software. And in the definition of the IEEE, it defines the process of analyzing a subject system to identify the system components. So we want to determine the components of the system and their interrelationships, and to create representations of the system in another form or a higher level of abstraction. And this is what we are trying to do. We're trying to get the high level design, low level design, and the detailed design. Now, um, uh, another important um, reason for reverse engineering is, what if the SRS is missing? What if we don't know what are the functions that this software is doing? Then we have a bigger problem for reverse engineering, because we have to extract from the behavior of the software what is the function it is fulfilling. So the importance of SRS is emphasized here. Without the SRS, we don't know what's the main functionality of the software we are dealing with. So supposing you are just given the the running software, let us say the binary of the Bobolin. Of course, uh, without the source code, or without the SRS, we don't know exactly what the Bobolin is doing. But but running the software, we should and also looking at the code, we should be able to extract the functionality of the software. But that takes a lot longer time to analyze and review. So we could see from how the Bubble-in software behaves that it allows um, taking of tests, multiple kinds of tests. It doesn't allow any unusual operations, unusual um, uh, activities on the mobile device while you are taking the test. You also have to extract from the behavior of the software that it supports the teachers creation of the test, managing of tests, and viewing the scores of the tests and other things that it can do. Okay, so that's a much harder task to do to determine the software requirements specification. So the SRS is a very important document to keep in order to maintain the software. Okay. All right. So I end my lecture for today. As I said before, be safe and be healthy. See you on Wednesday.